All right, so I'm recording. Like I was saying, so out of a lot of the topics that we cover, I usually consider this to be one of the lower priority topics. The reason for that is the way I kind of phrase it is we're setting the stage. When you get to organic chemistry, you'll get a lot deeper into what we're talking about. But what I want to do is just kind of lay before you, like, these are general trends. And that's all I'm looking for. I'm not trying to be overly specific. I'm not trying to be overly, detailed. It's like, here it is. You're going to do more of this in organic. And so that's kind of how I want to start off the lecture. So what we're going to look at is effectively the first part is going to be asking, if I take a compound off the shelf, especially a salt, and I add it to water, will it affect the pH? The reason why I found this important is because I've messed up my own experiments by not heeding these rules. I realized that I messed up the pH of my experiment and killed my experiment by not following these rules. So that's why I want to go over them. And then the last part is going to be talking about the structure of molecules. Why are certain molecules acidic, whereas others aren't? And so that will be the two topics we cover today. So what I want to start with is talking about if I add a salt, right, to solution, a salt being a ionic compound, when dissolved in water, separates into cations and anions. Our question is going to be then, will the cation or the anion affect the pH? And that's what we're going to address now. So what we're looking at first are things that I pull off the shelf, like salt, any kind of salt. I add it to water, and they're going to make a neutral solution. What does that mean? It means it doesn't affect either hydronium, and it doesn't affect hydroxide concentrations. So when I break down something like, say, sodium chloride, right, table salt, or even you go down to the ocean, right, most of it's sodium chloride. When you drink seawater, you don't get sick because it's acidic or basic. You get sick because it's too much electrolytes is what hurts you. So that's one thing. Okay, cool. I have electrolytes, too many of them. It's not changing the pH. Why doesn't it change the pH? And that's the question we need to ask. So cations from strong bases. So if I looked at sodium chloride, my cation is going to be sodium. Sodium could, if I wanted to, link it up with hydroxide to make a strong base. So theoretically, the Na is coming from NaOH, even though in real life it probably doesn't, right? We need to do a theoretical experiment. It's saying that that sodium, the Na plus, is so weak that it is not attracting OH or NaOH. That's how weak of an acid or a base it is. Why is it weak? Because it came from a strong base. We can apply the same idea to the anion. The anion of sodium chloride is chloride. Theoretically, let me do this right, that chloride could have come from messing that up again. Do that better. Could have come from HCl. So it used to be strong. It was a strong acid in terms of HCl. That's one of the four I had you all memorize. So the chloride is so weak at being a conjugate base that it doesn't want H or OH at all. It's so weak, it doesn't affect the pH. So that's the take-home message right now. If you have a cation from a strong base, like sodium, potassium, lithium, etc., or an anion from a strong monoprotic acid, like chloride, bromide, iodide, nitrate, chlorate, right? These are going to yield neutral solutions. What I want to hear back from everyone right now is, Was that a good explanation? Do we need to go deeper? That's my question to all of you. All right, I'm going to take silence as a good thing for right now. Take home message, right? Strong cations, so cations from strong bases don't affect pH. Anions from strong monoprotic acids don't affect pH. So what about salts that do affect pH, right? That's the next thing we need to talk about. So in the last example, when I gave you something like sodium chloride, the Na came from a strong base, the Cl came from a strong acid. What happens if it's not equally divided between strong and strong? If I take the example of NH4Cl, ammonium chloride, the chloride itself is still following the same rules of that last slide. It came from a strong acid, so therefore it is a very, very, very weak base, effectively not affecting the pH. If I look at the cation though, NH4, that is the conjugate acid of the weak base, ammonia. And so getting our terminology right is going to be critical. When I say very weak, it means effectively not an acid or a base. When it is a weak acid or a weak base, that actually still means it's acidic or basic, right? It's semantics, and I know it's annoying, but NH4 is a weak acid of the conjugate base NH3. Because it is a weak acid, it'll be between, around 4% dissociation or a little bit less. But I could theoretically write a chemical reaction. So NH4 donates an H to H2O, becomes hydronium, and then results in ammonia. We take a look at what's a product. Hydronium. Hydronium is going to increase the concentration of hydronium, obviously, which is going to decrease the pH. By how much? I don't know. We'll need to do work on that. It is definitely going to have an effect, though, on the pH. So I'm going to clear the screen, and we've gone over 2 of the 4 conditions so far. How do we feel right now? Do we need a better explanation? Do we want to go deeper into it? What is your feeling?
Could you possibly go slightly deeper?
Mm-hmm. Yeah, and so I know I kind of kept that vague. I was talking about deeper. What explanation do you want? We can go very deep. We can go deep. Like, it depends. Like what's throwing you off, I guess, is the question I'm asking.
Maybe just like slightly more in depth, because just with like the terminology, it kind of loses me.
No, I agree. It's tough. So if I was gonna do, let me try switching to a get out of this. I'm gonna switch my screen share to just a blank document, and I can write on it if I can find it. Apparently, I don't have one open. Give me 2 seconds. Let me just open one up real quick. Then I'll share it. All right, let me do that. All right, so you were asking to go a little bit deeper in terms of, getting confused on, is it strong? Is it weak? Is it very weak? Is it very strong? Right? It's vague, right? The example that I gave you was something like ammonium chloride. So the ammonium, right, is going to be a weak acid. Why? The reason for that is because ammonia, let me fix that, reacts with water, and it's going to form ammonium and hydroxide, right? And so if I know this is going to be my Lewis acid, my Lewis, keep getting ahead of myself, my Bronsted-Lowry acid, that means NH4 has to be my Bronsted-Lowry. Sorry, oops, I screwed that up again. My bad. Sorry, NH3 is our Bronsted-Lowry base. NH4 is my Bronsted-Lowry acid. This is the cation I'm looking at because I'm looking at this particular cation as part of the compound. It's a weak acid, right? So I could set up, theoretically, a new reaction where ammonium is now acidic. It could react with, we have at least 55 molar of water. It's a huge amount of water. One of those H's gets donated to the water. That will form hydronium and it will leave behind ammonia. I formed hydronium. If I form hydronium, my pH goes down, right? So it is a multi-step process, and I know it's not intuitive in the sense that you can see it in one step. It takes a lot of critical thinking, right? Number one, I recognize, okay, ammonium, that's my cation. Where does it come from? It comes from being the Bronsted-Lowry acid or the conjugate acid of ammonia. If I drew out a reaction of ammonium with water, it would produce hydronium. So in a very convoluted way, NH4 produces hydronium, which decreases the pH, making it acidic. I feel like I may have gone off on a long tangent on that. I hope that made sense. If it doesn't, let me know. I'll try to do a better job. So I didn't see who asked that question. I'm just trying to.
Yeah, that makes a little bit more
A
sense.
little bit more, like I'm saying, like it's not, this section is not easy. But again, it's going to come up in orgo. Like I said, if we can set the stage and we'd be okay with these ideas, that's all I want right now. The reason why chloride doesn't affect the pH is chloride is so weak as a base that it's not going to affect anything. So that's why ammonium, so it's not very weak, it's just weak. Weak still affects pH, and so the pH doesn't get affected. So I apologize if that wasn't the best explanation. It's tough, doing the way things we're doing now. But like I said, if it really is a problem, we can meet during office hours. I'm more than happy to try and re-explain things. All right. So why don't we finish off? Not finish off. We still got a couple more slides. We're getting there. So this might go a little bit smoother. But again, if you need explanations, let me know. So we've talked about salts that are neutral, salts that result in acidic solutions. We're now down to salts that yield basic solutions. The example that I'm giving you is sodium cyanide. And so again, we have to do that backing up process. We need to ask ourselves, where did the cation come from and where did the anion come from? The cation could theoretically have been potassium hydroxide. Sorry, not potassium, sodium hydroxide. So therefore, it's going to be a very strong base. So the cation, once it dissociates, is very weak. And that's what we have here, very weak. CN, cyanide, comes from the weak acid HCN. And again, this is where I think where phrasing gets a little confusing. Remember, weak acid is still an acid. It's only when it's very weak we don't consider it an acid. So maybe it's semantics. But HCN is a weak acid. So therefore, CN minus is a weak base. The weak base can interact with water, abstracting a proton, becoming HCN, and leaving behind hydroxide. Because hydroxide was left behind, it is changing the pH. It is going to increase the pH or increase the basicity of the solution. Again, I know it's tough. Is it making more sense, less sense? I'm trying to get a reading is what I'm trying to get from the room. All right, so I'll take silence as hopefully a good thing. I know it's not always good, but it's very difficult to read the room. I'll do my best. Another thing, it was just kind of funny, it's anecdotally, that I was watching, we put on, basically, what we've been doing to fight the quarantine is watching a bunch of James Bond movies here. We watched Skyfall the other night, and they were talking about eating a cyanide tablet and dissolving your teeth. The reason why it dissolves your teeth is because cyanide is a weak base. Not to say anything else about killing you, but yes, it is a base. It will destroy your teeth if you eat it. So kind of anecdotal stuff, but back to science. So everything I've given you right now has been 3 different conditions. One where you have NaCl, so it's, the conjugate acid and base of both strong acids and bases. We talked about having like something like ammonium chloride. So you have the conjugate acid of a weak acid, so ammonium, and then you have the very, very weak base chloride. So we have an acidic solution. We talked about sodium cyanide, cyanide being the conjugate base of a weak acid, so it's slightly basic. That makes a basic solution. What happens if you get an in-betweener compound? I have my ammonium, so we know that's the conjugate acid of a weak base, so it makes it slightly acidic. Carbonate, CO3, that's the base of a fairly weak acid. So we were talking about what happens when you get these salts of a weak acid with a weak base. How does this affect pH? Is it acidic or is it basic? And it's not very straightforward. What we're going to need to do is compare the Ka and Kb of each of the acid or the base. So ammonium carbonate, which I have here, we have ammonium and carbonate. All right. How does it react with water? Well, one of them behaves as an acid, one behaves as a base. Okay, both are affecting the pH. Who wins? If Ka, the value of Ka is bigger than Kb, well, the acid wins out, becomes acidic. So the hydronium ion concentration goes up, pH lower than 7. If Kb is greater than Ka, the base wins in that situation. Because the base wins, hydroxide is now in excess and the pH goes up, or the concentration of hydronium goes down. In the rare situation that Ka is approximately Kb, well, then nothing really happens. The pH kind of stays the same. So this is the hardest example, and it comes down to quantitatively comparing Ka versus Kb. So that ends this part, the first half of lecture. Like I said, if we're okay with what I've said, I think we're in good shape. How are we feeling is what I want to know.
Would we have to calculate the Ka and Kb for a problem like this, or would it be given to us?
That's a hard question to answer. I would have to give you like a lot of information to calculate Ka and Kb. It's totally doable. I'm not going to rule it out, but I mean, more than likely, I would give you the values of Ka and Kb, and you would need to know, okay, Ka is bigger or Kb is bigger. How does that affect the pH is what it would be. That makes sense?
Yeah, thank you.
I feel like that, I was a little bit hesitant. I don't know if that was a good explanation. Is that good enough, or do we want better?
Good enough. My Wi-Fi keeps cutting in and out, so I can just watch the recorded later.
Yeah, I was gonna say this. So the recorded video, I'm gonna pick between. I already did one at 10 and now one at 11. I'm gonna pick whatever is better, and it's gonna go up. So sorry if I cut out. Hopefully, what I have online is gonna make more sense. All right. So we're gonna move into the very last section of chapter 16. Um, Again, we're taking a bird's eye view. I don't want to go too deep into this. Like I said, this particularly will be a lot in organic. So again, we're setting the stage. Let's see if we can recognize patterns. And I don't want to go, insanely deep. Just let's start recognizing patterns, right? So what I see here is I have a list of halogen acids. Halogens being, iodine, bromide, chloride, and fluorine. They have an H on them, they're acids. What we notice is the acid strength increases as the amount of energy it takes to break the bond decreases. Why does this arise? Well, if we look here in HF, that bond is really short. That means the F has a very hard pull on that hydrogen. When we weaken bonds, it makes it easier for the H to pop off. If it's held on tightly, that means the H won't leave the HF and it will stay connected. If I look at something on the extreme like HI, hydrogen iodide, right? It's actually really more acidic because you can see the length of the bond has increased compared to HF. That means that I has a very or more weak pull on that hydrogen. That weakens the bond. If the bond is weakened, it makes the H more transferable and increases its acidity. So again, we're looking for patterns. As my electronegativity, not electronegativity, sorry, as the bond strength goes down, my acidity goes up. And so we can also talk, this is where I was getting a little bit over my skis a little bit when I mentioned electronegativity, but also as electronegativity goes up, the acidity also goes up. Don't worry so much about and you're going to find on the next slide, we say why. It's talking about the center atom, at least here. So when we see in our extreme example here, the CH4, right? If we look at the electronegativity between hydrogen and carbon, they're roughly the same. And that's why you see kind of like an even distribution of electron density. On the far end, we have HF, F being the most electronegative element. What that's doing, again, is pulling electron density onto that fluorine, weakening the bond to H. So as the electronegativity goes up, electron density is being pulled away from the H, which then results in a weaker bond, and then therefore the acidity increases. So how are we doing so far right now? All right, I'll take silence as a good thing. We're almost done. We're probably finished. Excuse me, I get the hiccups now. But we're almost done. We have a couple more slides, and then we'll be done with chapter 16. So what we were talking about in the last slide was increasing that electronegativity or weakening the bond to the H. So what I have here, there's my bond to the H, but oxygen's already pretty electronegative. It's almost playing tug of war with two strong people on one side. The O and the I are pulling in the same direction. The bond to H gets weaker. The O and the BR is pulling in the same direction. The bond to the H gets weaker. Cl and O, same thing. Pulling in the same direction, the bond to the H gets weaker. And so you need to think about, all right, making something acidic weakens the bond to H. How can I do that? Keep attaching more electronegative elements to that atom. And that's what we're seeing here. Chloride is way more electronegative than iodide. Therefore, HOCl is stronger than HOI. And we have more ways of increasing the electronegativity. Well, how do I do that? Keep attaching electronegative elements. There is 2 really electronegative elements. What could I do? Start attaching more electronegative elements, or more, or even more, right? As you start pulling more electron density away from the H, that bond becomes weaker and weaker and weaker. As it becomes weaker, it becomes stronger and stronger, right? 4 slides I've shown you, same take-home message. How do I weaken that H bond? If it weakens significantly, it becomes acidic. And as I weaken it further, it becomes more acidic. I'm going to skip that. That's kind of just like a summary. So actually, before I do the very last slide, any feedback or comments or anything that we've talked about so far in terms of acid strength, in terms of structure?
Can I just clarify?
Yep, go ahead.
So are you saying that, like, if you add more oxygen atoms, it makes the H bond weaker and then it's more acidic?
Yep, it's exactly what I'm saying.
Okay.
Yep. And so all you're trying to do is just pull electron density away from the H. As more electron density leaves, that H becomes easier and easier to remove, which then by definition makes it more of a strong acid.
Okay.
Cool. Anyone else need clarification or comments?
Does that only apply for when it's Cl or for any of the?
It's just the example I have. Cl
Oh,
just
okay.
make a lot of bonds. I mean, it could be I or bromine or anything like that. As long as you keep attaching more O's that are really close to the H, it's going to make that H bond weaker.
Okay, thank you.
Mm-hmm. All right, so let's get to our last slide. This is more foreshadowing again for another class, getting to inorganic chemistry, so beyond organic chemistry. This is important, and it doesn't really change any of our definitions. What it does is expand them. So nothing's changing. We've just expanded our definition. So instead of having an Arrhenius acid and base or Bronsted-Lowry acid and base, now we're going to talk about Lewis acids and Lewis bases. So it seems different. It says an electron pair acceptor is our acid, which I have in red. But if we take a look at that, that's technically the H that's being donated, right? Which makes it a Bronsted-Lowry acid. So it's still the same definition. Why is it a little bit different? Well, to make a bond, you need 2 electrons. When you get to orgo, you'll see why we have a double-headed arrow attacking. That's fine. We don't need to worry about that right now. But it attacks that hydrogen and forms a new bond. And that's what we see here. So new definition, same reaction. If I look at the base is an electron pair donor, which, if you put it on its head, is a hydrogen acceptor, right? So again, we haven't changed the definition, we've just expanded it. And so the example that I have here, yes, it looks like a traditional Bronsted-Lowry acid base reaction. When you get to inorganic chemistry or anything further than that, you start talking about electrons. So you can have an acid-base reaction with no transfer of hydrogen. It just happens to be a Lewis acid-base reaction. So instead of H's being transferred, electrons are being transferred. So again, it broadens that definition. And so that actually brings us to the end of chapter 16. So if you're fine with where you are, you're more than welcome to sign off. We still have 20 minutes technically. So if you want to stick around for questions, I'm more than happy. So just let me know.